A bank and a retail chain both say they run databases. But the way they use those databases couldn't be more different. When a customer logs into their bank account, the application looks up their account record by ID, checks their balance, reads the last 10 transactions. That's a handful of rows, retrieved by key, in milliseconds. When that same bank's risk analysts run a model overnight scanning every transaction from the past 5 years, grouping by merchant category, calculating fraud rates by geography, they're touching billions of rows and aggregating across many columns. Same database technology, fundamentally different usage patterns. The book names them precisely. The first pattern is OLTP online transaction processing. The second is Olap online analytical processing. These are not just different query types. They have different performance requirements, different access patterns, and over time, they've driven the development of different specialized systems. OLTP systems serve interactive applications and end users. Each query touches a small number of rows, typically a few dozen at most, looked up by key using an index. Writes happen constantly and must be fast. The dataset size is typically gigabytes to terabytes. These systems must stay highly available, because a slow checkout page or a failed login costs real money in real time. Olap systems serve analysts and business intelligence tools. Each query scans millions or billions of rows, but reads only a few columns out of potentially hundreds. The results are aggregations, total revenue, average order size, sales uplift during a promotion. The dataset size is typically terabytes to petabytes. Queries can take minutes or hours, and that's often acceptable. Here's the problem: running analytical queries on the same database that serves your users is a disaster waiting to happen. A long-running analytics scan that locks tables or consumes I/O capacity will degrade the experience for every user hitting your application simultaneously. That's why the industry developed a dedicated solution. The solution is a data warehouse, a separate database, completely isolated from the production OLTP systems, optimized exclusively for analytical queries. Here's how it works. Data is periodically extracted from the OLTP systems, databases, event streams, application logs, transformed into a format suitable for analysis, and loaded into the warehouse. This process is called ETL, extract, transform, load. The transformation step is where raw operational data gets cleaned, deduplicated, and reorganized into a shape that makes queries efficient. The warehouse is read-only from the analyst's perspective, no application writes go there, so analysts can run expensive queries without affecting production. The internal structure of a data warehouse follows a well-established pattern called the star schema, also known as dimensional modeling. At the center of the star is a fact table. Each row in the fact table represents a single event that happened at a specific point in time: a product was sold, a page was loaded, an ad was clicked. Fact tables are enormous. The book is explicit: companies like Apple or Walmart may have fact tables that run to tens of petabytes. Every sale ever made, every item ever scanned at a checkout, recorded as a row. Surrounding the fact table are dimension tables. Each dimension table describes one aspect of the facts: who, what, where, when, why. A dim_product table describes every product, its name, category, brand, price. A dim_store table describes every store, its location, size, opening date. A dim_date table encodes every possible date with pre-computed attributes: day of week, quarter, whether it's a holiday. When an analyst asks what were total sales in Q3 by product category, they join the fact table to the relevant dimensions. A variation called the snowflake schema normalizes the dimension tables further. Each dimension table can have its own subdimension tables. This reduces redundancy but makes queries more complex. Star schemas are typically preferred because the joins are simpler. Here's a number that changes everything about how you should think about storing analytical data. A typical Olap query touches only 4 or 5 columns out of a fact table that might have 100 or more. In a row-oriented storage engine, the default for OLTP databases, all columns from a row are stored together on disk. When you query for total sales by product, the database has to load every row: the product ID, yes, but also the customer ID, the store ID, the timestamp, the shipping address, the promotional code, all 100 columns, just to get to the 2 or 3 you actually need. Most of what it reads from disk gets thrown away. Column-oriented storage flips this: instead of storing all columns for one row together, you store all values from one column together. Every product_ID value lives in one file. Every sale_price value lives in another file. A query that only needs product_ID and sale_price touches only those 2 files, skipping 98 columns entirely. For a petabyte scale fact table, that's the difference between scanning terabytes and scanning gigabytes. Column storage also compresses dramatically better than row storage. Values in a single column are often repetitive. A product_ID column in a retail fact table might have only 50,000 distinct values across billions of rows. The book describes bitmap encoding. For a column with n distinct values, create n bitmaps, one per distinct value, with 1 bit per row set to 1 if that row has that value. Then apply run length encoding. Instead of storing a million zeros, store 999,847 times. These bitmaps can be extremely compact. Here's the elegant part: because the bitmaps are stored as sequences of bits, the CPU can evaluate where clauses using bitwise and AND operations that process 64 bits simultaneously in a single CPU instruction. Filtering a billion rows becomes a CPU-bound problem, not an I/O-bound one. Column storage transforms analytical queries from read everything, throw most of it away, into read exactly what you need, compressed, fast. What if the most common analytical queries are always the same? What if you know that every morning, the sales team asks for yesterday's revenue by product category, and every week the CFO asks for the prior week's revenue by store? You could run those queries fresh each time, scanning billions of rows, joining dimensions, aggregating. Or you could pre-compute the answers. A materialized view is a pre-computed copy of a query result, written to disk as if it were a real table. Unlike a regular virtual view, which is just a named query that gets re-executed every time someone references it, a materialized view is actual stored data. The query ran once, the results were saved, and future requests read from that stored result. The trade-off is straightforward: materialized views make reads faster and writes more expensive. Every time the underlying data changes, the materialized view has to be updated. In an OLTP system where writes happen constantly and need to be fast, materialized views are rarely used. In a data warehouse, where data arrives in periodic ETL batches and read performance matters most, materialized views make much more sense. A special case of materialized views is the data cube, also called an Olap cube. A data cube is a grid of pre-computed aggregates across multiple dimensions. Imagine a two-dimensional cube with date on one axis and product on the other. Each cell holds the total sales for that date-product combination. If you want total sales for all products on a specific date, you sum across one row. If you want total sales for one product across all dates, you sum down one column. Real data cubes span more than two dimensions: date, product, store, promotion, but the idea is the same. Certain queries against a data cube can be answered in microseconds because the answer was already computed. The disadvantage is inflexibility. A query that doesn't match the cube's predefined dimensions has to go back to the raw data. Materialized views in data cubes are optimizations, not replacements for the underlying column-oriented storage. Raw data is always more flexible, the cube just makes the common cases instant.